looking at this monostable multivibrator or oscillator circuit, and we so far we have seen that this circuit has two possible outputs or two possible states, you can say, and the output VO can be either positive or negative, plus V supply or minus V supply. Among these two, this is the stable output. So, if the output is positive at any point, then it will remain positive and nothing will and the output will not change. But minus output is not stable, because if ever the output is negative, then you see this negative output will try to make the capacitor voltage negative. Okay. So, it will draw or pump out current from the capacitor. So, the capacitor voltage will go down and down, and at some moment this voltage will be lower than the lower trigger point of this Smith trigger, and when that happens, the output will switch to positive. This is because this is a inverting type Smith trigger. Okay. So, once this is positive again, now the capacitor voltage will start to increase, but it will not be able to increase beyond 0.7 volt or the forward voltage drop of this diode, because after that, even if this is positive, the current will bypass through this diode and will not come to the capacitor and will not charge the capacitor beyond 0.7 volt. Okay. So, this is what we have seen. And then an interesting question that we asked is that if positive output is only the only stable output, then can we ever make the output negative? And we said yes, we can do it forcefully. How? Say if we connect a negative voltage directly at this point, okay, then Vp will be negative, it will go down no matter whether this is positive or not, because this is a direct connection. So, this voltage will go to the negative value directly, and therefore, this can become lower than Vn. Okay. And say if Vn is 0.7 volt at some moment, and if you make this negative sufficiently negative, then this will be lower than Vn, Vp will be lower than Vn. So, if this is lower, output will be negative. So, in this way forcefully we can make the output negative. Okay. But then so yeah, we have to make Vp negative forcefully, then Vo will be negative, but soon it will come back to positive output, but soon it will be positive again. So, and okay, and there is another alternative. Instead of connecting the negative voltage directly here, okay, and this negative voltage connection, this we call triggering. Okay. So, when you connect this switch, the output of this circuit is triggered to become negative, and after that in a short time it will become positive again. Okay. This is called triggering. And so, how to trigger? call this switch K, close the switch K to trigger the this bit trigger, and if K is open, then triggering doesn't occur. Okay. There is another possible modification of this triggering arrangement is this. See, instead of having this, what we do, we will apply a voltage here. Okay, say call this V T. Okay, and V T can be positive, negative, 0, anything. So now, if V T is equal to 0, then I mean this is like grounded. This is the normal circuit that we had here. Okay, so V T is ground equal to 0. So this is the normal, I mean usual state, usual condition. And if I make V T less than 0, V T equal to negative, okay, sufficiently negative, then this is like triggering the this Smith trigger. So this is the triggering. Why? Because you see that this voltage Vp, okay, Vp can be written as this is basically some sort of average of Vo and Vt. Okay, so we can write this is equal to VOR1 plus VTR2 divided by R1 plus R2. Okay, so you can find this expression by first finding this current. No current flows in this branch, so this current is VO minus VT divided by R2 plus R1. Okay, that is this current, and after that you can get this voltage here by adding R1 times the current plus Vt. This way you can find this. So this is the voltage at this point, and this is equal to VO R1 by R1 plus R2 when Vt is equal to 0. So this is the normal condition, normal feedback with this grounded, and this is equal to, this can be equal to some negative value if Vt is negative, sufficiently negative. So, if this is negative, then even if this is positive, if this is large enough compared to this, then the total combination can be negative, and when V p is negative, then this is lower than V n. So, then this can be lower than V n. So, V t negative will make V p less than V n, and therefore, V o equal to negative, output will be negative. So, this is called triggering. This way we can bring the output to negative value, and then it will not stay there for a long time, it will go back to positive value. Okay. So, let us draw some timing diagram. So, this is time, and say I draw V t, okay, and what else is important? Let us draw V c, that is important. V c, what else? Output definitely. V o. Okay. So, let us see how it works. Say at some moment this voltage V t is 0, it is kept 0. Okay. If this is 0 and say initially also V o is positive, okay. Say if V o is positive, means equal to plus V supply, V o is positive, then what is going to happen to V c? Say we start with some initial value of V c. Once again, the initial values are just assumptions, you can start from any value you choose. Say I choose V c starts from this. Okay. So, if it is starting from this value, then this is positive here. So, that means this is positive plus V supply, V c is starting from a negative value. So, it will try to go to plus V supply. So, it will try to go to this range plus V supply. So, it will try to go there exponentially like this, but it will not reach there, because once this voltage is greater than 0.7 volt, this diode will be on and the entire current will flow through the diode. So, this will not reach beyond 0.7 volt. So, this is 0.7 volt, okay. Although this is not in proper scale, 0.7 should be much closer to 0 than V supply, but okay, for this for now it is okay. So, it will just reach up to this 0.7, and then it will not increase any further. So, then it will stay at that value, okay. It will stay at that value forever. This entire current goes through this. So, capacitor is no longer charging. So, V c stays at this value, and this V c is same as V n. This is V c, which is same as V n. So, this stays at this value forever. Okay. Now, say at this moment, after a while, I make V t negative for a brief period like this, sufficiently negative. Okay. So, till then, this P c will remain at this position, output will also remain at that value up to this moment. Okay. And at this moment, what will happen? This V p will change. Okay. This V p will, let me also draw V p. V p. So, you see in this part, this V p will be also flat, because here V p is same as this output multiplied by this potential divider fraction. So, this is VO multiplied by R1 divided by R1 plus R2, because Vt is 0. So, Vt is 0 means only VO will decide this voltage. Now, here in this region Vt is negative. So, Vt negative means it will make Vp also negative, okay, for this brief period. If this is negative, this will also become negative because of this expression. This is negative, so this is negative. Now, if this is negative, then you see Vn was here. So, here Vn is Vn is positive, Vp is negative. This will cause the output to go to negative V supply. Right. So, the output will go to negative V supply, and let me just erase this a bit. Okay. Now, when the output is negative, okay, then what happens? So, now you see, so in this region, say let me call this equation 1. So, here equation 1 is valid. Okay. So, now you see VO is negative and Vt is also negative here. So, these two negative things will make or keep the Vp to negative definitely, because VO is now negative and Vt is also negative. So, these two together will make Vp negative. So, it will stay there. Now, after a small while Vt is becoming 0. Okay. So, after this moment, so if I come here, Vt is 0. Okay. After this point Vt is 0. So, here this term will be 0, but now you see VO is already negative. VO is already negative because VO has gone negative. Now, therefore, Vp will still remain at the negative value, not as much as before, because now Vt is no longer negative, only VO is negative, but anyway the combination will still remain negative. Okay. So, this is how it will be. It will be less negative once this VO has reached 0, and it will remain like this. And if so, you see Vp is lower, Vn is, if Vn is at this point, so Vn is higher, so output may remain negative. But there is another thing which has started to happen by now. What is that? That is the fact that this negative voltage is now making the capacitor negative. Okay. So, this voltage will therefore come down, will try to come down towards minus V supply, minus V supply. So, it will try to come down to this value exponentially like this. Okay. But at some point it will reach the lower trigger point. If this is the lower trigger point, okay, if this line is the lower trigger point of this Smith trigger, okay, and you see this is coming below lower trigger point. Therefore, here output, where is my output? This is my output. Output will become positive again. And once this output becomes positive, Vp, this voltage will again go back to this value, VO R1 by R1 plus R2, where this is positive V supply. So, it will come back here to this height and it will remain there forever. This will also remain there. And now what happens to the capacitor voltage? This is positive. Okay. So, just you do the analysis on your own, that is better. Don't please do not listen to me, because if you just blindly listen, you will not follow it really. So, do the analysis yourself. If you find any difficulty, then check with my analysis. Okay. Okay. So, we were here that output is positive, VO is here negative, and sorry, not VO, VC is negative, output positive. So, this positive value will now bring the capacitor up to a higher voltage. So, it will now come up, but how much? Up to 0.7 volt only. Okay. Because after that, this diode will get short circuited or open. So, entire current will flow through the diode and not through the capacitor. So, this will remain there forever like this. So, this will remain there forever, output will remain positive, this will also remain there forever, until and unless I give another trigger at some point. Okay. So, this is the timing diagram. If I give say another trigger here, then the entire thing will repeat again. Okay. So, you can just copy this thing like this. Similarly, here it will go negative, and then like it will repeat from this point. This also will repeat. Okay. So, if I mark this as point A, here this point B. So, point B onwards, everything you can just copy from point A onwards. Okay. Great. Okay. Now, if you have understood this, let us ask some interesting questions. So, question number one. Okay, I think the most important question you might be thinking of is that what this is useful for. So, what is the use? What could be the use? Use or application. Okay. So, it can have many uses. I will just talk about only one. This can be used as a pulse generator. What is a pulse? First of all, what is a pulse? A pulse is a voltage like this. Okay. So, this is say initially 0, and for a brief while it goes to positive. So, this is called a pulse. Okay. Similarly, this can also be a pulse. This is a negative pulse. So, this type of voltage pattern is called a pulse, and if this pulse is very narrow and the area under this is finite 1, in that case we call it an impulse. Impulse is a special type of pulse, you can say, where the duration is very small, but the area is non-zero. Although the duration is small, that is an impulse. We are not talking about impulse now, we are talking in general about pulse. Okay. And so, we can also have a pulse train, which means a repeated sequence of pulses. This is a pulse string. And this type of signals are often very useful in many experiments in laboratory to generate the sequence or this train of pulses. Okay. So, just like we need a function generator which can generate a square wave, we or triangular wave, we also sometimes need a pulse generator, pulse train for some experiments. Okay. So, this is also like a rectangular wave. Okay. This is also like a rectangular wave with duty cycle not equal to 50%. Okay. So, to generate this type of pulse train, we can use a monostable oscillator circuit, which we have seen like this. So, we can use a monostable oscillator or multivibrator, it is also called can use a monostable multivibrator to generate pulse train. How? So, the scheme is as follows. So, let me draw the block diagram. So, what we will do, we will take a square wave generator, function generator, and we already have studied this thing. So, you know how to generate a square wave. So, if I go back, you see this chapter we started with a function generator where we could generate a square wave here. So, take a square wave generator. From this you can take a differentiator, we have studied integrator, but not differentiator. I will talk about it soon. And from this, you connect this to a monostable multivibrator or oscillator. So, this will together generate a pulse train. How? So, signal here at this point, how does it look like? It is a square wave. Okay. Now, what is the function of a differentiator? You can guess, as the name suggests, it will just differentiate this function. Okay. It will differentiate this function. So, the output here will look like this. Let me draw them on same axis. Say this is the square wave, this is here. Okay. Then if I differentiate this, what I get is this 0, because here it is 0. So, flat horizontal line derivative is 0. Here you will get a pulse, positive pulse, because this voltage is increasing, and then here again it will become 0, because here it is flat. Then there is a decreasing slope very high. So, you will get a negative pulse or maybe impulse, you can call it, and then again 0, and then like this. So, this is the voltage which we have here, and this goes to the monostable multivibrator, where it goes to the trigger. Means it goes to this point, right. So, you see here we are applying this voltage, which is normally 0, but periodically it becomes very high positive and very high, I mean negative. Now, this negative pulses, these are the important things that we will consider, will act like this pulses. Okay. There are also these positive things, I mean like this here. Okay. And I request you that you please think yourself and be satisfied with the fact that this will not have effect, any much effect. Okay. So, this will not be effective, only this negative pulses will cause this capacitor voltage to vary like this output to vary like this. Okay. So, if you have these pulses, then you see the output of this circuit varies like this. So, here we will have the output which will be like this. So, here it goes to negative, it stays at negative for some time, then it goes to positive, stays ever until and unless next pulse comes, next negative pulse comes, and so on. This is the voltage that we will have at the output. Okay. So, this will be a pulse train, negative pulse train. Okay. So, this way we can make a pulse generator. Great. And then now if what if you want a positive pulse train instead of a negative pulse train? What can you do? The simplest answer is just feed it to a inverting amplifier. An inverting amplifier will change the sign of the voltage, right? That's simple. Okay. So, you make change the sign of the voltage using inverting amplifier. Now, what else you may need? Suppose, okay, so if once you say change the sign of this voltage, you will get this. And this is the 0 level. Okay. So, you see the pulse train is normally negative and it goes to positive sometimes. But what if you want the pulse train with the pattern like this, where this is the 0 level, so this is the 0 voltage level. So, how can you come from this to this? Okay. So, this could be an interesting question to talk about. Okay. So, let us talk about this briefly. So, this is like a DC offset addition, right. So, this is DC offset addition. Now, how can we realize this? Do you know? There are many possible solutions. So, one possible solution which comes in mind first is just an adder circuit. Okay. What is an adder circuit? It is just like this. Basically, an inverting amplifier which has multiple inputs R1, R1, R2. If this voltage is V1, this voltage is V2, then output VO is equal to V1 plus V2 whole multiplied by R2 by R1. Why? Please recall that we have studied this during when we were studying digital to analog converter. We have studied this circuit. And let me just tell you briefly why this is so. So, this current, if this is V1, so this is okay, this is at 0 volt. Due to virtual sorting, this will also remain at 0 volt. So, this current is how much? This is V1 by R1. So, this current is V1 by R1. This current is V2 by R1. So, therefore, this total current here will be V1 plus V2 whole divided by R1. Okay. So, this is the current, and this current when you multiply with this resistance R2, that will give the voltage drop across this. Okay, that will give the voltage drop across this, and this is at 0 volt. So, what will be the potential here? It will be 0 volt minus this voltage drop. Okay, I will have a minus sign here. So, this is one answer. Another, there could be many possible solutions. Okay, so let us see another possible circuit, which is okay. Let us leave that. I think this okay, we can do it. Not that is not much different from this. So, we can do it, no problem. It is not difficult. So, let this be 1 voltage, and to this I want to add a DC voltage. Okay. So, let there be 2 voltages, and what I shall do, okay, let me draw it here. Let this be 1 voltage, to which I want to add another DC voltage. This can be plus or minus. Now, what I do, I take a potential divider, I take the output from here, and so what will be this voltage? Okay. So, this voltage will definitely be, okay, call it V1, V2, and if this is R1, this is R2, then this voltage will be V1 R2 plus V2 R1 by R1 plus R2. Okay. So, this will be the voltage here if no current is drawn. To make sure that there is no current being drawn, I will connect a buffer. So, this is just a buffer we have studied negative feedback. So, this will be the voltage at this point and similarly also at this point, because this is just a buffer. So, this way we can add two voltages. Now, among these two voltages, one of them is going to be this pulse train. So, what I can do is, let me take another buffer. Minus plus, and this be the, here I will have the pulse train. So, this will simply copy this pulse, this voltage from here to here. This is just a buffer. What is a buffer? A buffer is something which copies one voltage from one point to another, but without drawing any current. No current is drawn. That is the beauty. So, why is that advantageous? If no current is drawn, then whatever circuit is here before this pulse train, that is not loaded, that is not affected much, okay? Because no current is drawn. So, that circuit is not going to be affected. So, if required, I can put a buffer. And here what I will do is this, let me take another buffer. Maybe I do not need so many buffers, and here I will take another potential divider. Here I will give a positive voltage plus V something, and here I will give minus V. Okay. So, therefore, you see, if I change this jockey up or down, then the voltage that I have here at this point will become positive or negative. If I bring it up, it becomes more and more positive. If I bring it down, it becomes more and more negative. And this voltage you can again express as with this potential divider rule. Similarly, this multiplied by this resistance plus this multiplied by this divided by whole resistance. Okay, let me write R3, R4. Let me call this V3, V4. Then this potential is V3 R4 plus V4 R3 divided by R3 plus R4. Okay. So, you can bring it up or down. If you bring up, this voltage will be more positive, because then R3 is reducing and its effect, R4's effect will be more. Okay. V4 is negative, let me write this minus. Okay. Okay, fine. So, this way you can change this voltage. This is a DC voltage. So, this DC voltage comes here, and this DC voltage gets added to this V1, which is same as this pulse train, right. This is very similar to this circuit actually. I mean, I just have this buffer and these two buffers which you can connect here, and instead of having this inverting amplifier, I have this 1:1 buffer. This is very similar. Okay. And here I also have the flexibility to change the amount of DC offset. Okay. And sometimes we connect a capacitor here before the pulse, before we feed the pulse train to this capacitor will eliminate or remove any DC component that this may have. So, if we want to remove the DC component that it has, so that can be removed with this capacitor, and then with this voltage or with this arrangement we can add the desired amount of DC. So, any DC part that the original signal has will be gone, and the new DC part which I can control how much I want to add will be added. So, this is like a DC remover. Okay. So, you know that capacitor won't allow DC signal to flow or low frequency signals, it will allow only the high frequency signals. So, the proper value of the capacitor is to be chosen, that is another thing. Okay. Now, okay, the last thing that we may discuss is, we can do a small okay, let us take a small example problem. So, in this circuit, how much is the duration of the pulse? So, this is called the pulse width. Okay. So, let us compute the value of this pulse width. So, how can we compute this pulse width? So, you just observe that this time is the same time which is required by the capacitor voltage to go from 0.7 volt to the lower trigger point. Okay. So, this is the time required this is the pulse width. So, let us compute this time required for the capacitor voltage to go from plus 0.7 to the lower trigger point. Okay. Now, what is the expression of Vc, capacitor voltage here? Call this time interval, call this t. Okay. So, in the interval t, we can write Vc as a function of t, starting from this as my t0. Okay. So, this is t equal to 0. If I take this as my time 0, then I can write this is equal to, definitely it is going to be the target voltage minus target minus initial whole multiplied by e to the power minus t by tau, where tau is the time constant of the capacitor charging circuit. Okay. And the time constant is R times C. And here you see, since this voltage throughout is below 0.7 volt, that means this diode will remain off. So, this branch is non-existent, practically non-existing. Okay. So, only this R C is the time constant. Okay. So, now what is the target voltage? Target voltage is LTP. No, target voltage is not LTP, target voltage is minus V supply. Okay. It was trying to go to minus V supply. So, minus V supply, okay, and this is the target voltage minus, here we write initial voltage is 0.7 volt, or in general let us write it as VDF, forward voltage drop of the diode. Okay. Whole multiplied by e to the power t by tau, right. And from this we can write Vc at this point, call this t equal to W or Tw, okay, which is the pulse width here. So, here we can write Tw, this will be minus V supply minus V supply minus v df e to the power minus t by tau, and we know the value here will be is equal to LTP, lower trigger point. This is the value here after this pulse width TW. Okay. So, now let us equate this. So, from this we can write minus V supply, let us bring LTP here, minus LTP. This will be equal to, when I bring it on that side, this will be positive, minus V supply minus V df e to the power minus t by tau. Okay. And please check my calculation always if I am making any mistake. So, let us check the sign once again. This is minus, this is minus, and this is plus on the other side. And okay, so from this, from this I can just make it plus, 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 plus. Okay, and from this I can write V supply plus LTP divided by V supply plus VDF is equal to e to the power minus, and this tau is tau w TW. So, here minus TW by tau. From this I can write ln of the inverse of this will be TW by tau, and from this TW will be, tau is nothing but RC ln, the same thing. Okay. And so, now this is the pulse width, and the value of LTP you can find easily. LTP is how much? So, you see in this region output is negative. Output is negative. So, we will ask what is the value of Vn which will make the output positive. Okay. So, here we have this equal to minus V supply. If this is equal to minus V supply, then this point is at minus V supply R 1 by R 1 plus R 2. This is the voltage here. Okay, I am doing it quickly because we did it many a times, and therefore, you have to bring Vc lower than this voltage Vp, which is same as this. So, this is the lower trigger point. Okay. So, this is the lower trigger point, and so let us write it. LTP is equal to minus V supply R 1 by R 1 plus R 2. You can put this value here, you can put 0.7 here, VDF is approximately 0.7 volt, and now you can we can change R and or C to change pulse width. If we want to control the pulse width, make it small or large, we can change these capacitance. You can make it variable, you can make this variable, and then that will give you variable pulse width generator. Okay, I think this is all for this class. We will meet again in the next class. Thank you.